Hello, good day to everyone. So in this video, we are going to learn about the deconvolution method for seismic data processing. Obviously, we will look at convolution, how we convolve our wave from the subsurface geology, and what are the deconvolution operators we apply to the seismic data. So also we'll look at the correlation, cross correlation, and autocorrelation of the method. So let's understand the deconvolution method, why we need to apply the deconvolution method. So actually this is a step in seismic signal processing to recover such as high frequency, so which are actually attenuated during the wave propagation. Uh, then the second objective of deconvolution is to attenuate the multiple, or also another methods which we normally use for attenuate the or eliminate the multiples. So also the another objective to equalize the amplitude, such as in the trace or the seismic data. So in the shallow part we have the high amplitude, but when we go deeper down, because of the loss of frequencies, we have the low amplitude. So the deconvolution method also can improve the amplitude or equalize the amplitude throughout the trace. So another objective of deconvolution is to produce a zero phase wavelet. So sometimes when your dynamite data is a zero phase, but vibrosa is the minimum phase. So the deconvolution method also can be recover your zero phase wavelet. So the other purpose of applying the deconvolution are generally the effect, the wave shape. So deconvolution, or the it's also called the inverse filtering, and it can be improved the seismic data that were adversely affected by the filtering. Not the filtering which we are applying in the pre-processing, but the filtering is actually the earth material. So let's say if a wave propagate from one subsurface material, then obviously some of the frequencies will be filtered out. So let's say some high frequencies are filtered out, then the low frequency on the left. So that will be only transmitted. So the effect or the purpose of deconvolution is to improve that frequencies or a high frequency which was actually sent to the subsurface. So deconvolution also can be performed on the other type of data, such as gravity data, magnetic, or the well-up data. So this is not applied only in the seismic signal, but also in the other signal processing like image processing or some magnetic, gravity, all type of digital data, or either it's a graphical data, then we can apply the deconvolution. So here is one of the graphical example of the seismic wave. So actually in convolution method, we have major two input. One is your wavelet and the second one is your reflectivity. So in this case, in this example, so our wavelet is, let's say this is your seismic wave which start to propagate, and you have the reflectivity on the backside. So when this wave convolve with the geology, so reflections appear. So this is actually the convolution method. So when a wave come and hit to this geology, so the convolution happen over here. So the convolution will be recorded over here. So the output of this convolution, which is the wavelet, and the reflectivity is the short gather data, or this is actually the offset gather data. So over here the reflectivity in the sense of sync light, and the source was zero offset. So that's when we have the bow tie. So this is the outcome of your convolution. So if we look at the mathematically, so here actually we have the function. So one is your input function and the second one is your filter function. So filter function in this case is a subsurface geology, and this static sign is actually your convolution. Actually, this is not the multiplication, a simple multiplication. I'm also going to explain how the convolution is happening in digitally or graphically. So we need the output function, and we have two input function, which is input function in the form of source wavelet and the reflectivity function, as I mentioned in the previous figure. So what are the steps we have to apply? So the first step is to reverse the operator. So let's say if you have two input function, let's say this is the source wavelet and the reflectivity, so you have to reverse the operator on the source wavelet, then multiply the vertical element, then add the product of that vertical elements and shift operator one sample to the right, and repeat step 2 and 3. I'm going to explain these steps in this figure. So let's say you have the reflectivity function, this one, and you have the source wavelet over this one, half, -1, 2. So this is actually already uh, reversed like this one. So we have already reversed the operator. So actually the reflector. So if we see this function, which is the reflectivity function, is this one. So we have the +2 sign. So let's say this is your 2. So this goes here. If you have this 0 here, then you have the -1, then half plus half, and then 0. So this is the wavelet. So what we do, we convolve. So we have reversed the operator, so we bring it here. Then how we convolve with this and this one. So this step is to multiply this one. 2 into 2 is equal to 4. Then we have to bring our operator toward right. Then again we have to multiply the vertical element. So 2 into -1 is actually equal to -2, and 0 into 2 is equal to 0. So then we have to add the product. So -2 will left only here, then so on. So now here 2 into half is equal to 1, then 1, 0, -1 into 0, 2 into 0 is 0. So then we have half, and like this we have to go so on. Then we'll find this reflectivity function. So this is the convolution methods. How does it work? So now we have the 4. So over here you have the 4, -2, 1, 0, -2, 1 half, and so on, like this one. So this one is actually the convolution method. How does it work? Then there is type of deconvolution. So when the signal is convolved with the earth material, so as I mentioned, the high frequencies are absorbed. So it is necessary to improve this high frequency because we need the high resolution of the subsurface data, especially the temporal resolution or the vertical resolution. So during this convolution, we try to reintroduce this loss of frequency. Thus, the deconvolution can be considered as a inverse filter. So there are some deconvolution method, which is called the deterministic deconvolution, adaptive deconvolution, spiking deconvolution, predictive deconvolution, spike deconvolution, and surface consistent deconvolution. So we are not going into detail of each convolution method, but that one will be explained later on in some other video. So the function of the deconvolution is actually to compress the seismic wavelet in the recorded seismogram. So deconvolution also reconstruct the reflectivity function, and it's improved the temporal resolution like vertical resolution, and attenuate the reverberation, which is caused by the reverberation operators, and attenuate the short period multiples, like you have different type of multiples which has been discussed in the previous chapters. So these type of multiple also can be attenuated using the deconvolution, especially this predictive deconvolution method. Remove the multiples. Then we have the shortening of the signal, which can be deconvolved, and suppressing the noise, and we increase signal to noise ratio as well. Then to it is actually applied before the stacking process, because once we already stack the data, then obviously we will lose a lot of information. So we have to apply the deconvolution before the stacking. But it can also be applied to the stack data, but it's depend on your objectives. So if you're looking only on the temporal resolution, then it's okay to go for stacking data. But if you want to have better signal to noise ratio, or then you have to apply the before stacking. So now to understand the deconvolution, need to understand the elements of the recorded seismic trace, which we know in the previous lectures, and build the build block of the seismic trace is convolution model by deconstructing the synthetic seismogram. So before I'll a little bit explain on the seismic trace, how does it actually produce. So what happened when in the case of well-log data, so we have the sonic log and we have the density neutron log, so which is actually combination of neutron density porosity log. So by these two method, actually these two curves or the information actually produce the reflection coefficient, which is called RC. Then this RC is actually convolved with the wavelet, which is the impulse response. Then we can get the synthetic seismogram. So another types which are correlation. So correlation also is very important to understand. So the correlation is actually the measurement of the similarity or the time alignment of two traces or two time series. And there is also another keyword which is cross correlation. So cross correlation is actually the name identifier or the reflects the name. So the cross correlation measure how much two time series resemble each other. So let's say if you have trace 1 and trace 2, so if we cross correlate each other, these traces, then we can see how much it is similar, or what are the similarity in these two traces. So it is a statistical measurement used to compare two signals as a function of time, or the shift is actually your time lagging. I will explain the lag of the time shift as well. And the another terms which is used, the autocorrelation. Autocorrelation is actually the correlation of a time series with itself. So let's say if you have one trace, then you will autocorrelate with itself. So it's a special case where the signal is compared with itself for velocity of the time shift. So let's see. I'll give you one example of this one, and it's particularly useful for detecting the repeating period within signal in the presence of noise. So let's say if you have the signal and noise, then you do cross correlate this wave, so you can differentiate the signal and noise. Normally the signal is cancelled out and your noise is cancelled out and signal is improved in autocorrelation. So let's say we have two traces or two wavelet, which is wavelet 1, 2, 1, minus 1, 0, 1, and the wavelet 2 is 0, 0, 2, 1, minus 1. So actually this is similar, but you see there is a lag of 2. So once we correlate this wavelet 1 with wavelet 2, so wavelet 1 comes on the top and the wavelet comes at the bottom. So the correlation method is slightly different than the convolution method. I will explain that one. So here you have to observe that if we correlate from 1 to 2 or 2 to 1, then what are the difference? Actually, the output is similar, but you see there is a lag. The maximum correlation occur at the -2 lag. So this lag is 4, but here you see the lag is 0. So the maximum correlation occur at lag 2 to have the maximum similarity of the wavelet from 2 to 1. So now here is autocorrelation. So what we do, we correlate autocorrelation of the wavelet 1, which is given here. So this is 2, 1, minus 1, 0, 0, 2, 1, 2, 1, minus 1, 0, 0, and 2, 1, minus 1, 0, 0. So what happened, actually what we do, we multiply the vertical element. So this and this. In this we are not reversing the operators or the wavelet. So we just keep it like this, and we multiply the vertical element and add the product. So add the product of this vertical element. So let's say 2, 0, 0. So it's come, output is -0. Then we have the 2, 0, 0, 1, 0, 0 is mean 0. So there is nothing. So in this case, in correlation, we multiply the amplitude spectrum and subtract the phase spectrum. So now moving to the Wiener filter, which is one of the very important filter used for seismic data processing, and it can be effectively remove the random noise. So it gets over the limit of the Fourier transform. So some noises still cannot remove in the Fourier transform, so we have to apply the Wiener filter. So by comparing the denoising results of the Fourier transform methods and the Wiener filter methods, the Wiener method filter is prior to the traditional method. So in Wiener method, what we do, we involve the designing of the filter, which is actually we have to find the least square error, which is our L, between the actual, this is the actual data, and the desired output. So this is desired output and the actual data. So we have to find out the least square error. I'm going to give you an example of the Wiener filter. So how does it work actually graphically? So what we have the input wavelet and we have the desired output. So what we do, we cross correlate this desired output and input wavelet to get the Wiener filter. So the another thing which what we do, we have the input wavelet and we autocorrelate this wavelet, and this comes to Wiener filter. Then the input wavelet also directly come to this stage, and this Wiener filter is convolved with the actual output to get the desired output. So here is a mathematical expression. So what actually we have the input function we already known. So we know the input function, and the output function also we know that what is the subsurface geology. So we need a filter which is to get the desired output. So let's say in graphical way, what we have the input waveform and the filter operator. And so what we get this output. But our desire is this one. So we need the zero offset or like this trace. So we'll keep changing this filter operator until we get this desired output. So this is a function of actually the Wiener filter. So there are some examples which I'm going to show before deconvolution or after deconvolution. So this is one of the real short gather. So this is before convolution and this is after deconvolution. So you can see in some part, let me zoom, highlight this one. So if you look at this closely to the arrow, so you see the higher frequency, this is before and this is after. So the higher frequencies are preserved in this data. Even if you focus on this section, so this is before, this is after. So you see multiple reflectors has been appears. In here you have only 1, 2, and 3. It appears to be better, but if you think logically, so this one is better because you have multiple layers, 1, 2, 3, 4. So this one is after deconvolution. So this is that was the short gather. Now when we stack this data, so this is before and this is after. Let me highlight. So over here I'm just going to give you 2 examples, so you can focus on this red arrows. So over here this is before and this is after. So you see multiple reflectors has been appeared. In this you don't have. This is before and this is after. So if you focus here, this is before and this is after. You see the continuity of this reflector is changed. One more example of deconvolution. So this is without deconvolution, is from Robert Sherrill. So let me zoom it in. So this is before and this is after. So let me highlight quickly. So this one is a before without deconvolution and this is with deconvolution. So if you focus here, so you can see there is not multiple reflectors appears. But after this you can get the vertical resolution high. And if you look at this one closely, I mean you just look at this one. So this is without deconvolution and this is without deconvolution, and this is without, before and after. So you can see this 2 reflectors appears. This is looks like one reflector, but here you can have multiple layers are appearing. So I hope you have understand the deconvolution method, which was a very important topic. So with that's all, thank you so much and have a good day.